What if I told you the coldest place in our entire solar system isn't Pluto? It's actual our moon. Near the moon's south pole lie craters so deeply that sunlight has never touched their floors. Not yesterday, not thousands of years ago, but for billions of years. These are called as a permanently shadowed regions. I'll show you. This is always a permanently shadowed regions. Or as a PSR says, the temperature can drop below 100 kelvins as well. You can see hundreds of craters on the moon which has a temperature below hundreds of kelvins, making them some of the coldest natural environments known. Scientists believe this frozen crater may hide something incredibly valuable: water. Not liquid water, but frozen water ice buried beneath the lunar surface. See this Faustine crater. And if that's true, it could completely transform the future of lunar exploration. Why water matters? Let me answer this. Think about it. Every liter of water, like every liter of water launched from Earth cost an enormous amount of money. Enormous amount. Like say this article, one article shows $22,000 just to carry 1 liter of water. But if astronaut could extract water directly from the moon as well, here also you can see that ISS requires 12 gallons of water each day, and it's 83,000 per gallon, and enormous. But if astronaut could extract water directly from moon, they could drink it, grow food, produce breathable oxygen, and even split it into hydrogen and oxygen to create rocket fuel. Instead of carrying everything from Earth, future missions could live off the moon itself. This concept is called as the in situ resource utilization, as called as the ISRU by NASA, and that's exactly why ISRO introduced this challenge. The challenge sounds simple: find ice. But in reality, it's one of the most complex planetary science problems. We must identify surface ice, subsurface ice hidden beneath planetary permanently shadowed craters, differentiate actual ice from rough rocky terrains as well, choose a scientific, valuable yet safe landing location, design an optimal rover path as well, and estimate how much ice actually exists beneath the surface. All using Chandrayaan radar, 2 radar and imaging data. Hands off to Chandrayaan. Fortunately, ISRO has already given us incredible scientific laboratory in orbit, which is Chandrayaan-2. It's DFSR, or what DFSR is called as a dual frequency synthetic aperture radar, which allows us to investigate between the lunar surface. While the OHRC, if we talk about the OHRC, orbital high resolution camera captures the okay, here's the OHRC. Optical high resolution camera captures terrain details with remarkable precision. You can even go see the images we have been using in our patterns. This is the remarkable precision of the images. While the OHRC or orbital high resolution camera captures terrain details with remarkable precision. Together, this dataset allows us to investigate places where sunlight never reached. Among all of the near the lunar south pole, one stands out, which is Faustine crater. Yes, sir. Which is Faustine crater. Inside this permanently shadowed region lies an even smaller crater as well. This is exactly complete a Faustine crater, and this is a small crater inside it, which we call it as a doubly shadowed crater. Imagine a crater inside another permanently shadowed crater. It receives almost no direct sunlight. No direct sunlight. If nature wants to preserve water for billions of years, this would be one of the safest places. Now comes the real challenge. If sunlight never reaches these craters, how do we actually see what's underneath? The answer is radar. Unlike visible light, radar. Okay. Unlike visible light, radar waves can penetrate the lunar surface. Okay. As these waves bounces back, as well we can see this radar images. As this waves bounces back, their polarization changes depending on the material beneath it. Like if I show you something, this look like this. Just a second. Okay. As this waves bounces back, okay, if I show you how the radar works. Okay, let's see. As the okay, let's see it like this. As this waves bounces back, okay, their polarization changes depending on the material beneath it. Okay. Decades of planetary science researchers shows that when the circular polarization ratio (CPR), this I want to say this, circular polarization ratio (CPR) is greater than 1, and degree of polarization, you can say this, degree of polarization gets to 0.13, the probability of subsurface ice increases significantly. Even colored pixels, almost say this, even colored pixels on our heat map is not just a color. Mm, it's a scientific probability. Thus, every pixel you can show shows a different science behind it. I'm very curious to learn about it. Now, research part. We didn't rely on assumptions. Okay, let me show you. Basically, we don't want it to rely on just on assumptions. Every major decision inside our system is supported by published planetary science, from radar interpretation, okay, from radar interpretation to permanently shadowed regions, landing site evaluation, rover navigation. Our solution combines existing lunar science with modern AI powered analysis, many of the things. This was a rover path analysis. Now, the main thing. This is Lunar, an AI powered lunar mission intelligence. AI powered lunar mission intelligence platform. Instead of opening multiple scientific tools, mission scientists receive every critical insight in one place. Let's imagine Chandrayaan-2 has just transmitted fresh observations. Within seconds, your dashboard highlights potential ice regions, detection confidence as well, landing opportunities, rover accessibility, and essential ice reserves as well. It takes time all because of it's too heavy. A single image of this Chandrayaan-2 consists of 2.5 gigabits GB of this single image, and to process it, it's require very high computation. That's the reason we use Colab for it. Uh, yeah, it's loading. But you can see what we put it as simple as we could put it. This is the ice probability heat map. And this is a DFSR image. DFSR image generates, and this is the actual zoomed image of it. Okay. We don't have to bother for this image how it looks like, but the DFSR image what we see actually for our safest landing site or ice prediction, and for all that. Blue region indicates increasing probability of subsurface ice. Okay. The green marker represents our recommended landing sites. The yellow path is our optimal rover traverse path. Okay, let me show you the path. This one. Yeah, this is quite annoying that it's just straight, but A star algorithm just works like that only. The yellow path is our optimal rover travels path, and then the blue marker identifies our target, doubly shadowed crater. Then this is our radar analysis. Moreover, you can see this here, I guess. This is model performance, how accurately the result was. This was a radar analysis, so I guess landing scope and so on, for terrain ice detection. Yes, and every single map generates an detection statistics as well. Terrain analysis, if I go for terrain analysis, it's landing on the moon. It's just about science, okay? It's just not about science. It's about survival as well. Using OHRC image and imagery and digital elevation models, we analyze crater morphology, slope, surface roughness, boundary density, and illumination. You can see that surface tensions and all that. Illumination, because every small slope can determine whether a mission succeeds or fail. A natural question arises: if ice is here, why don't we simply land here? Okay, if ice is here, why don't we simply land here? Directly land on it? Because the safest scientific location isn't always the safest landing location. Listen carefully. The safest scientific location isn't always the safest landing location. Our algorithm evaluates multiple constraints simultaneously: terrain stability, slope, distance, hazard, communication, and accessibility. Many of the things. The selected landing site balances scientific value with a mission safety. Okay. Finding ice is only half of the mission. Actually reaching it, it's actually important. It's equally important. Our rover planner doesn't simplify calculate. Our rover just don't simply calculate it. Okay. The smartest path. Avoid the slopes. It have to avoid the slopes, poor illumination, and unnecessary energy consumption as well. This significantly improves mission reliability. This is the volume of ice, depth of the ice, and as well. Okay, suppose the rover successfully reaches the target, as we can see in this image. Target. Now, another question appears: is there enough ice to justify the mission? Using radar backscatter model and dielectrics assumptions, our framework estimates subsurface ice concentrations within approximately the top 5 meters of lunar rivers. Now let us make this like this simple. Yes. Exactly. Using radar backscatter models and dielectric assumptions, our framework estimates subsurface ice concentrations within approximately the top 5 meters of lunar regions. Okay, providing valuable information for future resource utilization as well. Now, Now comes the backend architecture. Everything you have seen so far is powered by an intelligent backend pipeline. Let's quickly look behind the scene. Mission data enters for Chandrayaan-2. Okay. Mission data, the Chandrayaan-2 provides us the strips of that image. We provided in this. Our pre-processing engine clears and aligns a radar and optical imagery next to it. Now we have been used tons of image processing to it, and increasing the contrast, cutting out the edges into 800 by 800 pixels of the images, and then radar processing. Using CPRs, we extracted the CPRs and DOPs for it. Okay. Terrain analysis evaluates crater geometry and surface safety. Machine learning combines the scientific parameters to estimate ice probability, but till now we has been just applying for a single image. Machine learning, we are working on it for the node of 100 images at a single time. It requires us a couple of hours now to analyze just single image and completely process that single image. We are working on it as we wanted hundreds of images in just an hour, less than an hour. Now the path planning algorithm generates a safe rover traverse path. Okay, we can see this. It's a computer data set has been put in a single file. Finally, okay, this is the path has been generated. Finally, all outputs are integrated into a unified visualization platform for mission scientists. Okay. This is the final output. Just a second. Okay. See this. This is the final report it generates. But it's just a theoretical coded language. We're gonna be presented in this reports. A perfect report we're gonna be downloading. Yeah, again I want to tell you it's start work slow because of the high computational power it do required. Next thing I would like to say about the innovation. Our innovation lies not in analyzing one data set, but in integrating. This is a data set we're going to be evaluating. Hazard map, terrain analysis, slope map, and whatever. It's everything. Mission report if you could open. This is the mission report. Okay. Yes. Yeah, I was talking about the innovation. Our innovation lies not in analyzing single data set, but in integrating the complete lunar exploration workflow as detection, terrain understanding. Let me show the presentation. Analysis. Ice detection as well, terrain analysis as well, rover navigation, and many of the things. And resource estimation as well. Inside one intelligent decision support platform, like this one, everything in just a single platform. That's what we're saying. There's no architectural diagram of it. Let's talk about the future scope. Although developed using Chandrayaan-2 observations, the framework can easily be extended to future ISRO lunar missions, including LUPEX. LUPEX is a new mission from the ISRO. Autonomous robot exploration as well, AI assisted mission planning as well, and long term human settlement as well. And moreover, coming up, we can't discuss it here. For centuries, you can see, for centuries, the moon has inspired human imagination. Today, it changes human coldest craters hidden beneath its coldest, like, sorry for I'm just shaking it. It challenges human engineering, Okay. Today, we challenge is human engineering hidden beneath its coldest crater. May lie the resources that enable humanity next giant leap of it. Okay. With Luna eyes, with our Luna eyes, you can see this. We we are helping transform scientific observations into real mission decisions. Because because the future of lunar exploration won't depend only on reaching the moon. It will depend on understanding it. Thank you. See you in the next video.